All right, today we're going full on cosmic detective. We're pointing our virtual telescopes way out there, 5,000 light years away, to investigate a real mystery. Our subject? A very peculiar star named Pulsar B0835-41, and it seems to be hiding its secrets in a strange, flickering code. And this is really the heart of the investigation, the big question. Imagine a lighthouse spinning with this perfect, unwavering rhythm, and then suddenly it just goes dark. No warning. Now, what if that lighthouse was actually a star? What in the universe could cause that to happen? So, before we can really dig into our prime suspect, we've got to survey the scene. And in this case, that means getting our heads around one of the most extreme objects in the entire universe, the pulsar. Okay, so what is a pulsar? Well, it's what's left over after a giant star goes supernova. It's this tiny, super dense core, and it's spinning at just mind-boggling speeds. As it spins, it shoots out these powerful beams of radiation, kind of like a lighthouse. And if one of those beams happens to sweep past Earth, our telescopes pick up a little blip, a pulse of energy. And when I say regular, I mean perfect. The timing is so ridiculously precise that astronomers can actually use them as celestial clocks to study the universe. This perfect rhythm is what makes them so incredibly useful, but it's also what makes it so bizarre when they suddenly just stop. And this is the mystery we're digging into today. The official name for it is pulsar nulling. For reasons that we're still trying to figure out, a pulsar can just stop. The lighthouse goes dark, sometimes for just a couple of spins, sometimes for a whole lot longer. It's a puzzle that has had scientists scratching their heads for decades. All right, now that we've got the background, let's introduce the star of our show. Because not all these blinking pulsars are the same, and this one, well, this one is special. Our suspect, Pulsar B0835-41, is hanging out 5,000 light years away in the constellation Vela. Now, to give you a sense of just how far away that is, the light that we're seeing from it today actually started its journey to Earth right around the time the first pyramids were being built in Egypt. It's a long way away. So here's the case file. It spins once about every 3/4 of a second. That other number, the dispersion measure, basically tells us how much cosmic gas and dust the signal had to travel through to reach us. These are the basic stats, right? But the real clues to its weird behavior lie a lot deeper. So what is it that makes this pulsar so special? Well, our first big clue comes from how it blinks. This is where the detective work really kicks into high gear. So to even begin to compare how often these things go dark, astronomers use a metric called the nulling fraction. It's really simple. It's just the percentage of time the pulsar is off instead of on. Sounds like a simple number, but as we're about to see, it can be pretty deceiving. Let's put our suspect, B0835-41, side by side with another known nulling pulsar, B0809 plus 74. Now, if you just look at their nulling fractions, they look almost identical, right? Both are turned off for a little under 2% of the time. You think, okay, same behavior, but you'd be wrong. Because even though their total time being off is similar, the pattern is completely different. B0809 plus 74 has these longer, less frequent periods where it's off, but our suspect, B0835-41, it only ever seems to blink off for just 1 or 2 spins at a time. It's this rapid, almost nervous flickering. And this is the critical point, just like researchers have pointed out. That one little number, the nulling fraction, it doesn't tell you the whole story. The way a pulsar goes dark, how long and how often is a vital clue. And this specific flickering is our first major piece of evidence in this case. Okay, so let's move to our second clue and see how this builds the case. This one is really cool. It doesn't come from when the pulsar is off, but from the actual detailed shape of its beam when it's on. Every single time that pulsar's beam sweeps past us, it traces a very specific shape that we call a profile. You can think of this profile as the pulsar's unique fingerprint. It tells us all about the structure of its radio beam. Now, when astronomers look at B0835-41 using lower radio frequencies, its fingerprint is, well, pretty simple. It's just one big central peak. It's clean, it's straightforward, nothing too crazy going on here. But, and this is a huge but, when they look at the exact same pulsar, just at a much higher frequency, the fingerprint completely transforms. That single peak suddenly has 2 other peaks on either side of it. It becomes this complex 3-part shape.
So this is our next big puzzle. It's the same star, the same beam of energy, so why does its shape look so drastically different just based on the color of radiolight we're using to see it? What's going on?
The answer is hidden in the data. This number, the spectral index, it basically tells us how quickly each part of the beam gets dimmer as you go to higher frequencies. And look at that central component. Its number is way more negative, negative 2.2. That means it fades away much, much faster, which lets those side peaks, which were there all along, finally pop into view. Okay, we've gathered our evidence. We have two very distinct, very strange behaviors for this one pulsar. So let's put them together on the evidence board and see what kind of picture they paint.
So on one side, we've got clue number 1, a really strange, flickering, blinking pattern with only very short off states. And on the other side, clue number 2, a fingerprint that dramatically changes its shape depending on how we look at it.
For a long time, scientists might have just looked at these as separate quirks. Oh, that's a weird blinking star. And oh, that star has a weird beam. But the key insight, the big breakthrough, was realizing that these are probably two symptoms of the exact same underlying cause. They are connected. And together, these clues point to something massive. We're likely witnessing huge, system-wide changes happening inside the pulsar's magnetosphere. That's the incredibly powerful magnetic field that surrounds the star. The flickering, the changing beam, these are our windows into a dramatic reshuffling of energy in one of the most extreme places in the cosmos. So by piecing together these clues, astronomers aren't just solving the case of one strange star. They're actually probing the fundamental physics that run the universe's most powerful magnets. And it just leaves you with this incredible thought, right? If this one little lighthouse, 5,000 light years away, can teach us so much, what other cosmic secrets are just waiting for us, hiding out there in the dark?